So I'd like to thank Tony and Puri for inviting me to give this talk. I'm going to talk today about some, I guess I'll say preliminary work that we've been doing. So Tony and Puri and I run a center at the University of New Mexico that's focused on communication systems for exascale systems. Tony and Puri and Amanda are my co-investigators there. So I'd like to thank them for inviting me to come and present some of the work we've been doing, sort of figuring out what the challenges and opportunities in the future are for communication middleware like MPI. And we're pretty MPI focused. I am at heart an MPI person, but we're not purely limited to that. And since I stand between you and lunch, I'll probably be relatively brief today, but we'll see. So this is what I get for saying I know how to do PowerPoint. There we go. So just motivating issues. We've been looking at challenges for communication systems for exascale for quite a while. And when we sat down and we're trying to figure out what are the problems that really face MPI going forward, we started thinking about this from an application perspective. And that's something that, as a computer scientist, not a computational scientist, is not necessarily natural to me. And I had a lot of conversations with colleagues about this. But one of the applications that we were pointed at and settled on was in the general sort of coupled multi-scale physics space. And so I'd like to start by highlighting some of the communication challenges that we've run across talking to collaborators and colleagues at the national labs in this space. And in this kind of context, and this is stuff that the collaborators at UNM are working on as well, we're trying to simulate, for example, the interface between two fluids, both at a coarse scale because we have large scale volumetric fluid dynamics, and then fine grained interactions along portions of that system. And so one of the methods that's been proposed here, and this is a multi-scale method from Steve Scholar and his collaborators at the University of California, Davis, breaks the problem into two pieces. Right? So it has a large coarse scale fluid dynamics solver. So this is something like HiGrad or XRage, or pick your favorite, finite volume CFD solver that's running large scale 3D fluid dynamics problems, and you couple that with something that's trying to simulate exactly what's going on along this interface, right? So as opposed to throwing billions of points at the interface itself through an adaptive mesh scheme, you want to separate out the fluid, the tracking of that fluid interface as what's essentially a 2D problem, and solve that separate and couple these two codes together. And so there's lots of problems that come up in this space. So even looking at a CFD GPU solver on modern systems, we've seen cases where a regular mesh, not adaptive mesh, not regular mesh CFD solver, if it does the obvious thing, the application designers will spend 30% or more of its time in MPI. And there are a variety of reasons for that. One of that is GPUs have gotten so much faster that you start Amdahl's lawing away a lot of the computation. What you're left with is overhead, which is to say MPI. And that's potentially a problem, right? If we start spending 30% of our time in communication in what should be things that are pretty straightforward, like regular meshes, that becomes an issue. The Z model interface that Scholar and crowd pointed us at is FFT driven, right? So this thing spends all of its time doing FFTs. FFTs are mostly communication driven once you start going off node. We saw cases where it was spending 97% of its time doing FFTs, right? And so that's all of our time in all-to-all of these. There's a lot of opportunities for optimization there, as we've seen in talks about all-to-alls and all-reduces previously this week. And then we have to couple these two codes together, right? And there's all sorts of interesting communication problems there, ones that I don't really understand yet. And it gets harder. So if we start doing adaptive meshes or irregular communication, the communication problems become more challenging. We were doing some preliminary tests in this case where we were testing using MPI data types and using regularly packed data on irregular meshes. And MPI data types have challenges, but we were seeing cases where using MPI data types actually made things substantially faster because it let us use neighbor collectives, which gave MPI more information about how to move data around more effectively. Right? And they're like, well, this is we didn't know whether to be worried about this or very happy about this. But the fact that changing communication and in these regular meshes can cause a 20% performance variation or difference is one that is puzzling, or at least, again, is it something we should be encouraged by or something we should be concerned by? And that's something that we're still sorting out. And then finally, I was talking about the low order model being FFT driven. The high order model, which is what you really want to run for this fluid interface model, spends all of its time in a fast multipole solver. And that is really complicated global hierarchical communication, right? So if we're starting to do large-scale FFTs, large-scale fast multipole solves, that pushes on communication in lots of challenging ways too. And there's lots that MPI can do to help with applications like this. So this is a little adaptive mesh taken from the Clamor benchmark. But it demonstrates that there's even something simple like Clamor, there's all sorts of complicated data layouts, right? Arrays of structures, structures of arrays, arrays of structures of arrays, irregular data structures, dynamic communication patterns where who your communication partners are changes step by step by step, and hierarchical communication where we have a tree code that does an upward sweep, right, and does compute and communicate hierarchically, and has to assemble all of that itself by hand because that's not something that there's a primitive for today. And there are very nice hand-built bespoke approaches to doing this. So if you start looking at a lot of the sophisticated applications and libraries that exist, there are cases of, I think one of the more sophisticated ones I saw was doing neighbor discovery in an adaptive mesh code. And they had built a very sophisticated neighbor discovery algorithm out of RMA primitives, right? And hand-built this really sophisticated RMA exchange to basically find who are my neighbors to exchange data with. And these are very bespoke, very high performance approaches, but they're very brittle and they're hard to optimize and they're hard to maintain. And so these are the kinds of things where it would really be nice to have better primitives that made the job of maintaining these and optimizing these things easier. And there's lots to do in this space here. There's also lots to do in the hardware space, right? There's lots that the applications are doing that makes us say we really like better primitives. And as Rajiv and I discussed, I guess, yesterday, we have lots of primitives, but lots of times they're not used. And I'll get to that in a second. From the hardware side, there's also lots of reasons that we want to do this. We've seen this week lots of talks about GPU communication. And hardware is becoming more diverse and more powerful. So we've heard about DPUs. We saw proposals for stream-triggered communication in MPI, which are very, very encouraging. And the picture here is a trace of stream-triggered communication in the COMB Livermore benchmark using NVIDIA's libmp library. In this case, you can see, we're doing iterations. The compute in COMB is pretty trivial, but you can do the receive with stream-triggered receives basically on the GPU and have that immediately trigger off the compute on the GPU and turn around and do the next send from the GPU. And things lock up quite nicely. There's not large kernel launch overheads. Things fit together very well. This is one of the things that we would like to be able to enable, right? And the kinds of primitives that people are looking at that let us do. Right, and we don't be able to handle this. Things look different if you're communicating across GPUs in the same node. In fact, the bandwidth disparities are so large there. New optimization opportunities become possible when you're not just communicating over InfiniBand and you're communicating inside NVLink inside a node. But there's also some really gnarly problems that happen here. So this graph, right? So we're talking about the time scale here is about 30 milliseconds for this time scale, right? And so then we add in a nanosleep, right? It's top light yellow here. That's about 15 microseconds long right before we call receive. Same benchmark. Only thing we've added is a 15 microsecond sleep. The time scale of this graph is 2 seconds for the same work. And what happens, we just triggered the GPU into an unexpected message regime. So before, the send happened, the receive had been posted, the receive arrives at the GPU, everything is great. Here, we introduce a small sleep. we all know the unexpected message problems MPI faces on CPUs. When you start looking at unexpected messages in a GPU-triggered regime, you're putting a GPU into a place it really doesn't want to be, right? And so this impacts all sorts of communication trade-offs that we want to make. Like it impacts abstraction design a lot. If you just say, post your sends, post your receives, everything will be great, right? And we hope they're not unexpected. There are real problems to deal with here. And these are problems that we need to confront and make better for applications, not worse. Because going from something like this taking 30 milliseconds to taking 2 seconds, right? 2 orders of magnitude is really a bad number. And there is lots the communication middleware like MPI can do if applications let them. We started looking at these problems in the regular Halo space, right? Saying, what are all the various optimizations we could do for regular Halo exchange with MPI, right? And so we started with what's the baseline everybody does. All right, you look at what Fiesta, which is a shock hydro code from UNM that did, and it was doing the thing everyone does, which is sends and receives from user space. And we're going to do deep copies of Cocos array views from GPU space to host space, and then send, and then receive, and then copy them back. And that's how it takes 30% of your time in communications, because you're doing all this copying and back and forth. Obviously doing CUDA where it sends makes that a lot better. And I think they were able to get those times down with some help from us to the 10% range. You can do things like implicitly moving edges and corners, right? So as opposed to sending 26 messages for a 3D Halo, you send in the X direction and then the Y and then the Z, and you implicitly move the corners and the edges in 3 steps as opposed to 1. Is that the right exchange? Is that the right optimization to make? Right? That's a complicated trade-off, right? I mean, what's the kernel launch overhead to pack edges, to pack corners? Is it worth taking 3 steps of communication versus more kernel launches? Is that something MPI could do for an application? If you start looking at doing neighbor communication, right? We have neighbor collectives. Right? If we were declaring we want to do a neighbor collective for our 3D Halo, MPI could decide in theory to do that. In fact, if you look at OpenMPI, there is code in OpenMPI for doing 2-step neighbor collective exchanges that came from the original non-blocking collective implementation that Torsten worked on. It's almost never used because almost no one uses neighbor collectives. And there's lots of reasons for that. But there's lots of things we could do here. Many of them would require application changes. Hey, by the way, stop using MPI byte. Start using MPI data types. And that's an ask. You would like to have a good GPU triggering API. We'd like people to use neighbor collectives. And the sad story is that applications almost never let MPI do this. So the code here is from the ECP Copus Cabana particle exchange code. So this is a particle framework that was developed as part of ECP for doing molecular dynamics codes. And if you look at this, it's 2 for loops posting a bunch of I receives and a bunch of I sends, and the Cocos calls are in there to make copies and move data between GPU and CPU. This is a neighbor collective. This is, here are my neighbors, post a bunch of I sends, post a bunch of I receives, and wait. And the sad thing is, this is the right thing for programmers to do today, because they can't rely on neighbor collectives being implemented on the hardware they get them on the MPI they get from vendors. They can't rely, if they do get it, that it works well. This is portable. This is predictable. They know what this is going to do, right? Because CPU-based sends and receives and basic collectives are ubiquitous. They're portable. They're well tested. As Rajiv said yesterday, there's a chicken and an egg problem here, where vendors don't optimize primitives that applications don't use, and applications don't use primitives that vendors don't optimize. And so there's a lot of reasons why applications don't use these abstractions, and we need to find a way out of that. There are technical issues. Simple abstractions still perform poorly on some modern systems. And as a community, we haven't developed a good way to provide access to new abstractions that perform well on vendor applications and can be later folded into optimized implementations. So doom and gloom, right? So we have some good news. I think things have gotten a lot better. So I just outlined a bunch of problems in terms of abstractions drive data type, GPU performance, neighbor collectives, others that are here. And so both the community has been doing lots of good work, and I want to highlight some things that other people have done, and some things I think that we're doing that to address some of these issues that I want to highlight. And by we, I'm going to take the same approach Ron said. I'm a faculty member. I'm a middle manager. It means I don't do technical work. So this is mostly students and collaborators and staff. And so in terms of good news, I think it's worth highlighting that GPU data types have gotten a lot better, right? And I'll highlight how bad they were in about 2 slides. But both the MPICH team and some other people in the OpenMPI space have done a lot of work to make GPU data types pretty good, honestly. So in this case, we have we extracted a 3D mesh from a CFD code we were working with. This was from the Fiesta code, which is the shock hydrodynamics code being developed at UNM. This is a 200 by 200 by 200 3D array of 5 variables per point. So it's a 4-dimensional array. And we're going to measure IB latency just sending a face of that array between 2 nodes, right? And if we send a face in the YZ plane, this is C order, so this is contiguous memory. MPI data types outperform the blue bar, which is where the application just launches a Cocos parallel loop to pack the buffer itself, because it doesn't need to pack it, right? MPIs actually can do things here by deeply integrating the send through GDR copy down to putting data on the wire, and it works really well. In the XZ plane, where you start sending 200 pencils of data, things are not perfect, right? In this case, if we compare against the baseline of, all right, give me a Cocos parallel loop to pack a contiguous buffer and send that versus MPI sending with data types, you lose 20 or 30%. And that might be, 20 or 30% is something that's recoverable, right? If we have other optimizations we can do and data types are costing us some, and this can probably be improved, 20 or 30% might be something we can amortize away. That might be a starting point we can work our way past. And so there's a lot of progress that's been made here. There's still work to be done. If you go to the XY plane where you're not sending 200 pencils, you're sending 40,000 40-byte elements in your sparse data type, things get ugly. Right? There's still work to be done. But in a factor of 2, which is what we're seeing in both these optimized data type engines, is more difficult to amortize. But it's also worth highlighting that this is sort of the worst case for data type engines and MPI, because we've taken something that's very sparse and we're comparing against a baseline that's really easy for the compiler to deal with, right? If I say, here's a CUDA parallel loop for a 40 array to pack into a contiguous array, a CUDA compiler is going to just say, this is perfect. This is what I was built to do. And it knows that at compile time, and it can generate very tight, very efficient code to do that. If you tell an MPI implementation at runtime, hey, by the way, I have a new data type for you, figure it out, that's a much harder problem. In addition, we're sending over IB, right? And so our bandwidth difference between the GPU and InfiniBand puts MPI at a disadvantage. It's not worth pipelining the packing and sending here because InfiniBand is so much slower than the memory bandwidth of the GPU. And neither of the MPIs here try to, because they know that doesn't make sense. So there's little benefit from pipelining, packing, and sending, which might make sense if you're going GPU to GPU inside a node. So, these numbers don't look great, but this is probably sort of worst case for MPI. And these can be made better as well. Importantly, there's a difficult parameter trade-off space here. And this is where we get to predictability, I think, which is an important factor we need to think about. Real codes have better opportunities here. And there's some really interesting opportunities for MPI and compiler cooperation. And when we start looking at what's going on here, part of it is we're making MPI wait to the last minute to figure out what to do. Is there a way that MPI and the application could figure out how should you lay out your data so that MPI can work better and make this problem a little less awful for what we're asking MPI to do? As a quick aside, I'm a computer science professor, which means I have to teach students to read technical papers. So I would like to thank authors of papers who write things like speed up of 59,000 compared to vendor MPI as their baseline, because I need to teach students to read papers critically and to take things with a grain of salt. And so that means saying, what's the real baseline you should be comparing against? Is it an unnamed vendor's MPI that is much worse than either of these, or is it what the application would do by hand? So just an aside, I appreciate nice examples of showing my students. Finally, I think there's really important that we have ways to demonstrate the benefits of using these better primitives to applications. So there's lots of opportunities here. Neighbor collectives are those things that use data types, things that we've seen with stream communication, with aggregating collectives. We need to be able to have some way of telling application authors, if you use this primitive, this is how much better things could be. Because application authors have limited amounts of time, we all do. And if I say rewrite your whole communication approach to use neighbor collectives and data types, and they're going to want to know how much better will that make their life on a production MPI that they will actually be able to run on real systems. So one thing we've been doing in that space, and again, this is very preliminary, is trying to use machine learning methods to predict how changes in network performance might change application performance. So I could actually take an application, run it, do some profiling, do some measurement, and then say, all right, based on the work we've done, if we change from using that communication primitive you've been using to this other approach, this is how much faster your application would get. So it's worth your time to make this change. We've been quantifying these communication abstractions using roofline-like models and then using that to train machine learning models. That work is still in progress. The other place that I think this is really an issue is on the benchmark and mini application side, right? It's really hard to, full applications are great, right? That's the gold standard for making things better. It's a very hard place to do research, especially in academia, because giving a student a multi-million line piece of code and saying, all right, make it better is overwhelming. And so mini applications and benchmarks and proxies are useful. Most of the mini applications and proxies and benchmarks we have don't push on the kinds of applications that I was talking about at the start of my talk, right? Instead, they push on ping pong exchanges, and they push on regular Halo exchanges, and they push on regular Halo exchanges from irregular meshes. So we've been developing a few mini applications that well, in theory, should push on parts of MPI that current benchmarks don't. Beatnik, I named this high performance parallel interface model because hippie did not seem like a good idea. So it is a first implementation of the parallel interface model that I mentioned at the start of my talk. It's on GitHub. It's still in progress. It's academic researchware, buyer beware. You get what you pay for, everything like that. The low order model pictured at the right is simulating a Raleigh-Taylor instability, right? And this one, low order model is FFT bound. This is the one that just beats on FFTW and Hefty very hard. It's a very nice benchmark for pushing on FFTs. It uses a regular mesh decomposition. Next slide. The higher order method there, and same picture, this was a low order solve, requires a scalable far field force solver. And that means having some distributed spatial decomposition of points. Almost no benchmark that we have, no proxy app, mini application we have today in the open community provides that. And so we need a scalable non-periodic far field force solver. That means a fast multiple method that runs on GPUs. Having looked a lot, that's something that's just not out there in the open. It also means a spatial, not logical domain decomposition. So space filling curves across the mesh, which leads to other communication challenges. We would like to have this. We don't have it today in the open. If anybody has suggestions on libraries or codes that we could drop in here, as opposed to me having somebody who wants to do a PhD on yet another fast multipole solver, I would be interested in talking to you. Finally, we would like to couple this to a CFD solver. Right? That coupled communication problem is a really interesting one. And and we have CFD proxy applications out there, right? Mini Arrow and Lulesh and a variety of others are CFD proxies. What would be a good one to couple with this is an interesting question. We're examining primitives and frameworks to enable this coupling. So this is the general sort of high-level space that we've been working in. I don't want to take too much longer, but the one other piece we've been talking about that Amanda mentioned the other day is MPI Advance. And MPI is big, but the real challenge here for getting applications to use higher level primitives is really portability. That is, if I go on a machine that has, OpenMPI 1.6, because that's all that my IT people will install, and I still want to use neighbor collectives or aggregating neighbor collectives or something else, we need some way to provide portable access to better primitives that doesn't bottleneck us to how fast the forum approves something and then vendors implement it and then vendors make it work well. So the goal of MPI Advance is basically to provide early access to new MPI primitives and new MPI optimizations through overlay libraries that you can take and run on any vendor MPI. So if the vendor has that abstraction already and it runs well, you don't need us. You want partition communication? Go. You want aggregated neighbor collectives and they've implemented already? Good on them. But if your IT people have decided OpenMPI 1.4 is what you get, you can still drop in libraries that will provide those primitives for you that you know will work, will work with each other, and it provides a path to new C++ interfaces. So the current MPI Advanced implementation, and the GitHub link is here, includes a prototype C++ interface based on NPL. It includes partition communication. It includes the aggregating neighbor collectives that Amanda was talking about. This is not mine. I'm just advertising. So this is Tony and Puri and Amanda's work. I think this is a very nice piece of a very nice effort that I think they're looking for collaborators and more people to help with to grow the set of tools that are available. And the goal is to do no harm, right? So we should test and verify these various extensions versus each other and versus vendor MPIs so that you can run them and know if I use this primitive, I'm still going to be able to run even if the vendor MPI doesn't do what I need it to do. And it's going to be predictable and it's going to behave well. So with that, I'm about out of time. Acknowledgements. My co-investigators, Tony, Puri, Amanda. I obviously have lots of thanks to give there. Students and staff at Tennessee, Thomas Hines and Derek Schaefer at UNM. My students, a wide range of lab collaborators, and then funding from an NNSA PSAP award and an NSF award has funded a lot of the various things I've been sort of overviewing here. And you'll see again in the future because we have a bunch of papers in progress around the various things I've been describing today. And with that, I'd be happy to take any questions. And we'll see if chat has any too.
Patrick, can you hear me?
Yes.
So it keeps occurring to me, I may have said this to you before in various conversations, but what is the opportunity, especially when the data are resident in the GPU with really high bandwidth and indexing power, to ask the applications to consider, space filling curves or hybrid data structures that are not just the Fortran or C 3D array for regular problems? Is there really a value?
We can't hear on Zoom. That's old. Okay, good. Sorry.
I wanted to say, once you're in GPUs with loads of bandwidth and lots of compute power,
right?
Why couldn't I use at least space filling curves towards the outer edge of my domains and regular problems? And maybe I still use a simpler indexing form in the middle of my domain and my GPU. Why don't we ask applications to consider that as a way to trade off? Then your performance for moving the data would be enhanced. As a
middleware operating systems MPI guy, I think it's a great thing to ask applications, but it's probably not their first priority. And if you talk about, radically changing their data layout strategy and finding a scalable space filling curve layout that will do that, that gets into the applied math side of things, which is, that's where I just say, yes, as an MPI implementer, if I could make sure that outer edge was contiguous, or I could say, please try to give me data in pieces in chunks that are at least 8K in size, so I don't have to do IOVEX to pack all these complicated irregular data structures. That'd be nice. I don't know how realistic that is from the application point of view, though, and so I don't want to step out of my lane too much there. Scroll down. Okay.
There's a question on Zoom.
You mentioned applications that use neighborhood communication patterns on GPUs. Are there any applications that use MPA neighborhood collectives from the library? You mean from the MPI library? So we've tried it some. In fact, and the data types problem becomes an issue there, and it's not an MPI problem. There may be an opportunity there. The issue when you start using neighborhood collectives is that you can end up with very sparse data types, right? So if you end up with lots of sparse data that you have to pack, especially if you're talking about an irregular data structure, neighborhood communication patterns on GPUs. Are there any applications that use MPI neighborhood collectives from the library? I'm not sure I completely understand the question. I haven't seen it. I've implemented it by hand in some cases and gotten some reasonable results on CPU side. We implemented using the neighbor collectives in Clamor, including rebuilding the communicator every time step after the adaptive mesh refinement. And it worked remarkably well. CPU world. GPU space, I'm less sure about. And we were not running, okay, I think you answered. I'm glad I answered your question. I wandered into the correct answer somewhere along the way. That's a place that's a place we were trying things, right? So one of the things we're working on is really, we had this, I showed a spreadsheet of here are all the various optimizations we think you can do with regular halos. We're in the process of just implementing a chunk of those out and seeing what happens. And so that's going to mean implementing neighbor collectives in Fiesta and or Highgrad and seeing what happens. And that's going to mean having figuring out how that ties in with the data type side of things, because when you start doing some of those exchanges, they get expensive. Is there a way to hybrid that with application packing so that the application can partially transform its data and still do a neighbor collective from the GPU? I think there's interesting opportunities on the MPI primitive side there as well.
Patrick, I have a question. So thank you first for the insights also on the HydroShow codes. That's interesting. And also interesting that you mentioned Cocos. So maybe you are aware or not of a project that we are developing within the Cocos organization, which adds distributed views.
Yep.
So we have a project that exactly adds PGAS support to Cocos. Yep. So now you can allocate views that distribute and span over multiple address spaces. And those optimizations that you have mentioned, including data types, including the awareness of the architecture and the access patterns where they go, would you be interested in a collaboration where we would consider these considerations in Cocos views and as well as the other abstractions, which is traits and spaces? Because this is what we currently are looking into, and right now the view abstraction using elemental RMAs is not something
it doesn't
really
work
scalable.
Right. It works really well. I mean, I've seen the papers. It's really interesting work. Mm-hmm. It works really well inside nodes, right? When you have the NV link to move things around. Then when you start doing, 40-byte RMAs, millions of 40-byte RMAs to go off node, things are more problematic. No, I think it's a very good place to work. And I think for the MPI, there's a lot of opportunities at the MPI programming, performance portability framework, programming language interface that identifies, hey, look, these are the things that are really hard for MPI to do at runtime, right? And so data types are something we've been fighting as a community for a long time, and lots of good work has been done there. And I wanted to highlight the work the MPitch and Tempe and other people have done there. But there's only so much you can do at compile time. At runtime, when you have an arbitrary data type. You do runtime code generation, the templating systems that, the kinds of things that Cocos provide, that Raja provides, that all these other systems provide, I think is a very nice place to look. The other advantage of that is, and I think it's a good one, is it's a way to show impact more broadly, right? If you can provide an abstraction in a framework that lots of applications and many applications are using, you're not just demonstrating, hey, look, I made the Sandia ping pong benchmark fast, or I made, Mini Ghost or, your favorite mini app fast. We made this framework fast, and look, Trilinos got faster, and Hyper got faster, and all these other codes got faster. And it's a good path to taking optimizations and getting them into applications without having people having to rewrite the applications. You help rewrite portions of the framework that work underneath it. And I think it's a great place to collaborate.
Oh yeah, thank you. So right now we have the principal issue as the Trilinos has a very sophisticated abstraction of communication, and now competing with distributed views is the challenging factor here,
right.
Especially showing where it would scale and what the demands from the programmer perspective are to express something that would scale. Right.
No, in fact, the Trilinos communication abstraction looks a lot like the Kibana one I put up earlier in the talk. It literally is that sort of gather, loop a bunch of ISINs, loop a bunch of iReceives, loop a bunch of ISINs with a set of neighbors, and finding ways to help make that better through distributed views and other abstractions, I think is a very promising direction.
Thanks for the talk. So we've heard this chicken and egg problem, and I've heard people complain about how bad RMA is, and it doesn't, it's not as fast as you would expect, so no one's using it. How can we break this?
So, I mean, part of the goal behind Advance is to try to break that, right? Is to say you can get the primitives, you can start using them, it won't cost you anything. And then once applications start using them, it's easier to put them into acquisitions to say, hey, look, we have applications that are using these primitives now. You need to make them perform well. So, we have to have some way of getting applications, of letting applications use better primitives portably. And not just portably in terms of the code runs, but the code runs as well as it would have if they had implemented themselves by calling send and receive.
Okay.
So that's one way. It really gets down to, I think, you have to push on both the vendors to say, could you please, we are going to require you to support this primitive, which is yet another requirement in, is a hard thing to add. And you have to allow applications to use it and hold them harmless for doing so. That's the only way to break out of it that I see. If anybody has another approach, I'd be happy to hear it.
Well, are you planning on upstreaming the MPI advanced implementations into the major MPI
yes.
Distributions?
So our path there is that we do the work in MPI Advanced as a prototype. We have an MPI prototype called EXA MPI that Livermore and DOE are funding some of our work, and Los Alamos are funding some of our work on, where we can explore deeper integration of those prototypes down into the fabric layer, and sort out what the issues are there with pushing those abstractions down towards the fabric. And then from there, that's the next step is into an open MPI or an MPitch or something like that.
I'll be happy to help with that, yeah.
That'd be great.
Just want to add to this chicken and egg problems. And I think 2019, Ignacio did a good study, right? Looking at hundreds of MPI code.
Yep.
And he found that 40% are still using MPI 1, right? 80% is 2. I think so. I don't know what the answer is, that how do you break? All the middleware researchers are trying to do optimizing these, and application developers are not using. Maybe one way we train the faculty to teach students to use neighborhood collectives other than, and then it will probably, because if the developer don't use those features, right, then the production, they will not port it to the compilers and all those things.
Yeah, I mean, the training side is important.
So I think it's still true in 2019, 2022. I think still there are 40% still using MPI 1 and 80% using.
It's, I mean, I spent a lot of time, my students spent a lot of time looking in various ECP frameworks that people have written, and the number of times you see, oh, look, that's that MPI primitive that they're building by hand was sad. I mean, I don't know what it says, but it doesn't say it's not, there's a problem there. And I think figuring out how, as a community, we train, be it training application writers to do that, incentivizing them by saying, if you do this, this is how much faster things will get. I don't know the way to break that. It's not.
Yeah,
You
we
know,
see a lot of
using
things we
the
are doing,
yep.
and the primitive exists for the last 10 years.
Yeah,
Nobody is still using that, right? And doing that by hand. So
I agree.
don't know.
But we have to provide them both the knowledge and the reason to do differently, right? And the ability to do so portably. And that's something that, so it's.
One last question. I just want to comment on the chicken egg, how to break that. I think the number one barrier is not the performance, like, for example, MPitch or the implementation is not there, so people don't use it, right? I think the number one barrier is the ease of use. So when we put some new idea into MPI, we want to, we always consider, this in MPI, it's going to last for 50 years, or we will never be able to take out. So we made it very general. And when we make it very general, the interface become really, really complicated. For example, neighborhood communicator, it's a big, many pages to read and difficult to understand, and it's very cluttered how to use, right? So essentially, we are asking applications know that there are patterns, and basically, as you say, it's just a few lines of a for loop, right? But when they use in neighborhood, it translates into not less lines and more complicated concept. You are translating a specific idea into a more general idea, and you're making problems more complicated.
No, I agree.
Right. So one of the way out I'm thinking is, rather than focusing on the implementation, of course we need to do all front, right? But instead of first focus on the implementation and focus on how to get into MPI, maybe we need to focus on the meta layer, how the pre-processor layer or some library layer, so make it easy to use. For example, even user doesn't know neighborhood, right? If the library use it, like some common library or Cocoa layer, they use it, then people will use it.
Right. Well, and that's where I agree, and I think that gets to the point about providing support for this in abstractions like distributed views. One of the places that we started playing with neighbor collectives first was in Clamor, and that's because we could do it in a library that provided a much simpler, basically distributed cell array primitive to the application. We didn't have to go back and rewrite all of the exchange in the application. We just had to say, okay, here's the place where the library finds neighboring cells. Here's our neighboring cells. Here's our neighboring processes. Put those primitives in the libraries that then suddenly push into applications. I think that's a place there's some good leverage. And there are good examples of that. So we had an interesting conversation with somebody from the PETC team that was looking at a PETC scalable communication library, which is, we're seeing more and more of these sort of scalable communication libraries in portability frameworks. That's another path to getting better primitives in where there's a, but I think, but libraries, anyway, I think I agree, but I agree with you.
We need to somehow convince, for example, the way Cocoa doesn't use advanced MPI API because the performance is not there. They need to, get the performance first, right? So we need to get this to somehow convince them, even the performance is not there, please use it, then trust us, we'll get there.
If the performance is not there, I don't think they'll do it. I mean, it doesn't have to be better, but it can't be a lot worse. Ron. Okay. Well, I don't hold the stick, so I'll, So anyway, thank you, everyone.